In this video, we'll be looking at this idea of special vectors for a linear transformation or a matrix, and we want to make it more precise, and we want to figure out how to find these special vectors. All right, so let A be a square matrix, and let V be a vector in Rn. I'm going to take it to be non-zero. Then V is called an eigenvector of A if there exists a real number, lambda, in R, so that A times V is lambda times V. Then the real number, lambda, is called an eigenvalue of A. All right, I'm going to look at the same matrix we had in the last example, in example 3.1.1, give two eigenvectors and their corresponding eigenvalues for A. All right, so we already seen that if I take A times 1, 4, I get 1, 4. And so A times V equals V, that's, I could put a 1 here. So 1, 4 is an eigenvector with eigenvalue lambda equals 1. The other vector we had was minus 4, 1, and we found that this one gave 4 minus 1. So it is minus 1, that's why it was flip, times the original vector. And so the vector minus 4, 1 is an eigenvector. Its eigenvalues is lambda equals minus 1. So whatever is in front. All right, so now we want to know how we can find these vectors without help from outside. All right, so theorem 3.1.1 will tell us, let A be an n by n matrix, let V be a non-zero vector. V is an eigenvector for A corresponding to eigenvalue lambda if and only if V is in the null space, which is good because we know how to find null space basis and write it as span. So the null space of A minus lambda I. And so lambda is an eigenvalue for A if and only if the determinant of that matrix, A minus lambda I, is 0. All right, so let's do it. Let's prove this. This is a definition of an eigenvector. I'm going to start with it. And I'm going to find another way of writing it. So this is the same. If I send everything to one side, I'll get AV minus lambda V equals the 0 vector. Then if I factor V, I want to factor V out here, that's fine, but I can't have a matrix minus a constant, so I need to put the identity matrix. And so when I take this matrix and multiply it by V, I get 0. That's the definition of the null space. So V is in the null space of A minus lambda I. All right, so we now consider when lambda is an eigenvalue for A. So let's see, lambda is an eigenvalue for A if and only if AV equals lambda V for, it needs to be a non-zero vector, so a non-zero vector V in Rn. And so by 1, that means there is a non-zero vector in the null space of A minus lambda I. And so the invertibility theorem, well, that means the null space is not just 0. And so the invertibility theorem tells us that that's the same thing as A, not A minus lambda I, sorry. Let me put the matrix. That's the same thing as this matrix not being invertible, and so determinant of A minus lambda I is 0. So this is by the invertibility theorem. All right, so this is how we're going to find eigenvalues, by checking when this determinant is 0. And then when we want to find eigenvectors, we'll be looking at the null space of this matrix for those specific values that are eigenvalues. All right, so let's see. For this, we're going to need a tiny bit more vocabulary. So definition, characteristic polynomial. Let A be an n by n matrix. The characteristic polynomial of A is, it's going to be that determinant. So determinant of A minus something I, and I'm going to put x here. I mean, we want lambda for eigenvalues, but at this point, we're going to look at x as a variable, and we're going to see for which values of x we get 0. So the eigenvalues of a matrix A are the zeros of the characteristic polynomial PA of x of A. So let's try an example. I'm going to start with this matrix, 1, 4, 2, 3. I want to find the eigenvalues of A. So I'm going to look at PA of x, which is the determinant of A minus xi. All right, so we want the determinant of A minus x times I. So really we're looking at the determinant of 1 minus x, 4, 2, 3 minus x. All right, so we're really taking A and subtracting x from the diagonal elements. Well, it's a 2 by 2 matrix, so we can just compute the determinant easily. I need to find the zeros of this, so let's expand and simplify. If you expand, you'll get 3 minus 3x minus x plus x squared minus 8. And so I'm getting x squared minus 4x minus 5, and that's x minus 5, x plus 1. And so the eigenvalues of A are the zeros of that polynomial, and so it's going to be x equals minus 1 and x equals 5. Let's write it as lambda. The first eigenvalue is minus 1, the second one is 5. All right, I'm asked to find an eigenvector of A for each eigenvalue. That means finding an element of the null space of A minus that lambda I that isn't 0. Right? The 0 vector would always work in these equation here, but it wouldn't be interesting. All right, so let's work first with, I guess, minus 1. And so I want to look at A minus lambda I. So that will be 1, 4, 2, 3 plus 1, 1 on the diagonal. So I'll get 2, 4, 2, 4. That's going to reduce to 1, 2, 0, 0. All right, so I'm looking for something in the null space. That's the same as thinking of a homogeneous system. I have one free variable, which you should always have, otherwise it's not an eigenvalue that you started with or you made a mistake. And so my x is going to be minus 2s, my y is going to be s, so minus 2, 1s. And so I'll take s equals 1. My first eigenvector is minus 2, 1. This eigenvector is not unique. Any value of s except 0 would give you a valid one. All right, so now a minus 5i, that's 1, 4, 2, 3, plus minus 5, 0, 0, minus 5. And so I'm getting minus 4, 4, 2, minus 2. That reduces to 1 minus 1. Again, I'm looking at the homogeneous system. So I'm going to have a free variable here. X is s, y is s. So I get 1, 1 s. And I just like to take s equals 1. I get 1, 1. So we have two eigenvectors that we like. v1, which is minus 2, 1. For eigenvalue minus 1, and v2, which is 1, 1, for eigenvalue 5. Okay, so this is how you find eigenvectors and eigenvalues for a matrix.